All right, then. Thank you all for coming and to listen to us talk about enhanced sampling options on Anton 2 at PSC. This is going to be me, Avi Robinson-Mosier, presenting, and Michael Levine giving anything I've forgotten and helping respond to questions as the legitimate chemist in residence. I'm only a software engineer who sometimes moonlights as a chemist. So let me get started here. So all of the enhanced sampling features on the Anton 2 at PSC, or at least most of them, are backed up by an algorithm called time square sampling that was developed at DesRes. And it's an enhanced sampling approach that's sort of conceptually similar to simulated Hamiltonian tempering. And simulated tempering is kind of like a sequential version of replica exchange molecular dynamics, or REMD, which some of you are more likely to have encountered. Just to remind everyone what that is, REMD is where you set up a sort of a series of Hamiltonians, which have some overlap in their distributions. And you run one simulation of each of them. For instance, it could be a sequence of temperatures for a given simulation, going from 300 to 400 Kelvin or something like that. You run one simulation at each of the Hamiltonians separately, and then periodically you can exchange configurations between usually adjacent Hamiltonians if the conditions are right. And this lets you basically propagate information up and down your Hamiltonian ladder. So for instance, you've got something running at low temperature that's not going to cross energy barriers, and you got something running at very high temperature that doesn't really see the energy barriers, and it's going to go all over the place. And this can let you get at the low temperature sort of physical simulation rung information, transitions between states that you would have to wait a very long time to see transitions between if you were just running vanilla simulation at that rung. So that's REMD. Simulated tempering, instead of running a simulation at every one of the at the Hamiltonians, you run one simulation and it hops around in Hamiltonian space based on transition probabilities that are governed by its current configuration and also some kind of weights that you configure the simulation with for each Hamiltonian, which are generally related to what you think the free energies of each of the Hamiltonians are. The tricky bit with this is you have to provide these weights a priori, or have some way of like running for a bit with whatever your initial guess for the weights are, coming up with a new guess based on the simulation you ran, and then rerunning. So it can be somewhat onerous to get good simulated tempering simulations running. Time square sampling has built-in online free energy estimators. So it starts off with, you don't have to supply any initial guesses. And as the simulation runs, it figures out what it thinks the free energies are for each of the Hamiltonians. And actually, in some ways, it uses, if your guesses are wrong, that actually helps drive the sampling. So it's a kind of neat algorithm. We've been working on it for a while, DesRes. There is now a paper on arXiv about it. There's a link in the bottom left corner. I think these slides may be provided afterwards. So you can go look at it there if you're interested. The code that does it is also available on DesRes's GitHub. That's in the bottom right here, if you want to go check it out. But that shouldn't be necessary for running any of the things that you run at PSC. To sort of give an example of how these kinds of things are useful, like let's say you've got a energy landscape like the one in the bottom left here, and T1 is sort of your physical temperature, the one that you're interested in. If your simulation is where this little walker is in the bottom left, it's probably going to take you a while to cross into the higher energy well to the right because you've got this high energy barrier between them. And what you would like to see if you're trying to explore sort of the relative abundance between these states is to get a lot of transitions back and forth to get good equilibration. And this will take a long time at this temperature. If, however, you can run at a higher temperature, T2, where the effective, the energy barrier will appear lower, you'll get more transitions. You'll get a lot of equilibration back and forth, and be easily able to sample both of those energy wells. And then, like I mentioned before with REMD, if you have a way of feeding those configurations back down to your lower temperature, you can then basically appear in the higher energy well. And if your enhanced sampling algorithm has the right statistical properties, you should get the right balance of states between them a lot more quickly than you would if you were just trying to run vanilla simulation in that temperature Hamiltonian. The motivation behind developing something like time-square sampling, which is in the simulated tempering mold, such that it runs single simulation, was initially that Anton is really good at running single long simulations, but not so good at running a whole bunch of short simulations and communicating between them. So that's what motivated the algorithm, but it ended up having a lot of beneficial features even on top of that. Also, I wanted to say, in terms of questions, if people have questions while I'm talking, please write them in the chat, and I'll ask Marcella maybe to wait for a moment that it looks appropriate and like say stop me and say raise the question, or you can just hold your questions for the end and we'll address them then. Okay, so I've described sort of the underpinning of the enhanced sampling methods at Desres. One of the particular methods that we make available to people at PSC is something called tempered binding. That was the full description of this is in a PNAS paper referenced in the bottom left here, and you can go read more about it there. But in general, it's a method for exploring interactions between two bodies. That could be proteins, which is where this has mostly been studied, or it could be a protein and a ligand. But what this illustration here is sort of drawing out is imagine that you have two proteins here, and these dotted lines are sort of a conceptual illustration of interactions between bits of the proteins with one another. And if you run vanilla MD for protein-protein association, there's a decent chance that they'll come together, but not necessarily in the lowest energy conformation, and they'll get stuck there for a long time. And a lot of times when you're running this kind of interaction, you want to be able to either find the lowest energy sort of crystal state conformation, or be able to get a good distribution of the metastable states that corresponds to the like relative occupancies of those states. So the way tempered binding works is we have this set of this sort of ladder of Hamiltonians that we consider. Lambda 0 is your physical Hamiltonian, the one that corresponds to your real world situation. And the higher Hamiltonians are ones where it becomes increasingly disadvantageous for the proteins to spend time near each other. It's a combination of weakening their interactions from one protein to another, and setting the equilibria such that they should be further apart. So basically, it's making your van der Waals sigma increase and your van der Waals epsilon go down. And what this will do is when you run TSS with this set of Hamiltonians, rather than getting stuck in your metastable configuration, it'll spend some time in a higher lambda state, which will cause things to come apart and then come back together in a way that'll let it explore metastable states in a way that should be proportional to their actual occupancies in that low, in that Hamiltonian. And this is just a plot of what that lambda exploration may look like with respect to time. So you see it sort of spends a little time in the 0th rung, which is the bottom 0th Hamiltonian, but spends a lot of time jumping up and down and doing that sort of exploration. And you might be concerned that it doesn't spend very much time in lambda 0, which is probably where you care about. But because TSS does provide estimates of free energies, you can actually reweight the samples from Hamiltonians that are not lambda equals 0 to get you more relevant samples in that lambda equals 0 Hamiltonian, and use those to compute the occupancies that you care about. Michael, am I forgetting anything relevant here? Cool. Okay, so here's an example of using this and showing how it helps you escape from metastable traps. This is Barnase and Barstar, which is sort of a workhorse system for looking at protein-protein interactions. Barnase is in blue and Barstar is in green, I believe. And starting off here, this is a vanilla simulation, conventional MD. It's running for a fairly long time. You can see in the top left, this is like tens and hundreds of microseconds. And it finds a fairly stable conformation, but it's not the crystal state one, as you'll see in a moment, since we've overlaid that here. So this is metastable and hangs out for quite a while. So clearly you're going to need to spend a lot of simulation time if you want to even get out of this state, if you're just running vanilla MD. If we instead run tempered binding, it jumps around a lot. You can see it like comes together, comes in various conformations, and then reassociates a bit. I see something in the chat. We'll get to that in a moment. You can see this does match the crystal state pretty well. And the more adept chemists at Desres tell me that one thing that's particularly nice about this is even the side chain conformations are as they should be for the nicely balanced state. If this were a full tempered binding simulation, you wouldn't just see it permanently hang out in that state. You would see it explore other metastable states as well with the appropriate occupancies. Let's see, what was the question in the chat? Can you do weighted ensemble molecular dynamics on Anton 2? No, we don't provide that capacity at PSC, sorry to say. So I have talked about two forms of enhanced sampling that we make available at PSC, which are simulated tempering, which is most straightforward to do in the context of temperature tempering with the adaptive weighting from TSS, though you can also do simulated tempering of parameters that are not temperature. I've talked about tempered binding. You can also set up restraints between centers of masses of groups of atoms with a sort of target equilibrium distance and a relevant force constant. And you can do something similar with restraints based on the RMSD to a reference structure. And for both of these things, the equilibria and the spring constant can be tempered with TSS. So you can either, or they can be set according to a schedule. So you could just have something where you're saying, okay, let's pull these guys apart at some rate. Or you could have something more like umbrella sampling, where you say, let's explore what the free energy is based on distance between these two groups of atoms in some range. Like you say, you know, you want to look at them from 0 to 10 angstroms apart, and you say, okay, what is the free energy profile, of course, across that? If you do this with TSS, that will give you that profile. Similarly, for something like RMSD restraints, you could say, like, imagine you've got a protein where there's a loop that you know has two different conformations. You could do TSS where you have an RMSD restraint targeting a certain distance from one of the conformations at one end of your schedule and the other conformation at the other end of your schedule, temper between those, and see what the free energy profile is along that schedule. So there's a tool called PyTSS that both helps in setting up these simulations and analyzing them. There's documentation on the PSC wiki that's the link is referenced at the bottom of this slide. And I just want to talk through here a tool called Plot Basic that is the thing that is most useful for analyzing one of these enhanced sampling simulations and explain what the various quadrants of this plot mean. So when you're running enhanced sampling, you want to make sure that what you've done is actually properly converged so that the results you're seeing are meaningful. The plot in the top left is a histogram of the amount of time the simulation is spending at each of the different Hamiltonians, which we refer to as rungs in the context of TSS. So rung 0 is, you know, in the tempered binding example is the natural rung, and then rung 175 here would be the least interacting one. The blue bars are the histogram of occupancies that are actually observed, and the red plot is an estimate that TSS makes of what the histogram should look like if you ran for infinite time, sort of what the converged distribution of rung visits should look like. And you want those things to sort of, on average, match. It's okay that the histogram is a little spiky. That's normal. But if like all of the histogram weight were toward the left, where the red line were flat, that would indicate that things were poorly converged, and you would need to either change how your schedule is set up or run for longer. The top right is another view of the Hamiltonian/rung visits. This is sort of over time which Hamiltonian it's spending time at. And you kind of want this to look like a fairly dense scatter plot the way it does here. If it like spends a bunch of time at the top and then jumps and spends a bunch of time at the bottom, you probably have some slow degree of freedom that's going to give you some trouble with your convergence, and you either want to improve your schedule or just run a lot longer. In the bottom left is a plot of free energy with respect to rung, which is often the output that you're interested in. You can observe this in this plot. You can also use PyTSS to get a more, like just to get it out as like a data object that you can manipulate and do further analysis on. And in the bottom right is a plot of over time of the DG between the first and the last rung, which again is often something of interest. And the light blue background is an online estimate of the error in this observable. And you want to make sure that like that sort of two standard deviations I think we're showing in this plot reflects pretty well the actual amount of wiggling you're seeing in that estimate. And you can also use it for downstream applications. That is all I actually have to say about the enhanced sampling capabilities at PSC on Anton 2. Here's a survey link that's provided so you can go make comments on this, but now let's open it up for questions. I see something in the chat.
It was just me. I shared that survey link. Sorry.
Okay. So feel free to ask me to go back to slides and ask questions about them, or if you have questions for me or for Michael.
Okay, I'll ask a question since nobody else is.
Thanks.
So I've never done enhanced sampling. Do people usually do some unbiased runs beforehand to know if it's even necessary? Isn't that the norm?
I would say generally yes. Like, again, it depends sort of what you're interested in observing. But if, for instance, what you want to see is you want to get a good distribution among the metastable states, then yeah, I think it'd be quite reasonable to do a short run first and see if there even are any substantial barriers that you need to worry about. But, you know, no, go ahead.
Well, the whole motivation for me to use Anton is to get longer trajectories, and my trajectories to date have been only like hundreds of nanoseconds. And perhaps the barrier that I'm hoping jumps over just takes a little bit more time. And I don't really know the pathway either.
So is what you're hoping to see, like, do you want to figure out like the relative abundance of the states or like the free energy difference, or do you just want to observe a path transition, or what are you looking for?
My preference would just to know the pathway. I don't really care about the free energy profile.
Michael, do you want to say something about that?
Yeah, I mean, if you have an idea of what the states are from a previous simulation you've run or from crystal structures, I think the RMSD tempering method that's available can give you a kind of first approximation to the path. Generally, pulling things between states with RMSD doesn't give a great path, but it'll give you starting structures that you could, you know, simulate and see how stable they are and if they fall on either side of the barrier. So I think that's a pretty reasonable approach that you could use the stuff we have available on the Anton to do.
Okay.
But you'd run it for a while just to see what would happen, Michael, right?
Yeah, I think the running some vanilla first is probably a good start of the endpoints, and then you can run with the RMSD restraints to pull them between them.
Okay.
See a question in the chat. Would it be possible to use transition interface sampling and replica exchange transition interface sampling, like using Pi-Retis? I am not familiar with that. Could you describe a little more about how that works? If Gabriel, if you'd like to unmute yourself for.
Thank you for having my question. So Pyretis actually is just a library that uses the interfaces. So transition interface, it is basically the potential separating between the two barriers. It is run by vanilla MD, and then you later analyze using the Pyretis. So it's essentially analyzes the crossing probability for extremely small and nearly impossible brute force simulations like gas transition through membranes.
So is it something that like looks at the potential, like the free energy profile across, like if you have a membrane sort of in
And
your
you-
simulation, you see how what the free energy potential is, free energy is with respect to position relative to it.
Yes, for the gas passing through it, permeating.
Yes, you could. I think you can definitely do something like that if you do basically a center of mass group restraint and drag your thing across the membrane.
Mhm.
That should give you a basically a PMF, potential mean force across, or free energy profile across, with respect to position relative to the membrane.
I think for some of the path sampling methods where you don't have to apply any forces, it's more about generating the data and then having the right tools to analyze it. You can probably do it as long as you know what simulations need to run. If you have to do it adaptively, you're going to have to take data on and off the machine, which maybe is not super efficient, but you will be able to run the simulation component of it faster to do that. But for example, for this approach, like we wouldn't have the tools on the machine to do it online. But if you know what simulations you need to start for like short trajectories off the barrier, for example, you should be able to take that off the machine and analyze it separately. No problem.
Yes. The idea would be to have a huge, massive membrane that has a transmembrane protein within in the middle
Mhm.
that is responsible to capture those sort of climate change gases like CO2, methane, and having those gases added to the system and see it's permeating through either through the protein, either through the membrane, and then later doing the analysis using this.
Yeah, so I think
transition interface.
simulating it, generating the data on Anton, that makes total sense trying to do that. And then yeah, and it's better if you use an approach where you don't have to do anything online, if you can just generate the data by running the simulations. I think that sounds reasonable to try.
And to be clear, the thing I was describing wouldn't involve, actually, I was proposing, I guess, an alternative to using this method, which would be instead of running a simulation and then using this method to analyze it, I was thinking you could possibly do something where you just do essentially TSS style umbrella sampling with your group restraint on the gas, drag it back and forth across the membrane. Probably some of the time it would go through the channel, some of the time it would just go through the membrane, and then you could possibly get a free energy profile directly from TSS rather than from performing one of these forms of analysis afterward.
Yeah, that sounds as a good alternative.
I definitely suggest before you use your whole allocation, trying to generate the crossing trajectories that you see, you know, what the time scale you expect it to be is, because different
Yeah, this is-
membranes with different pressure profiles will have different kinetics for like even small things crossing them. So it'd be good to figure out what you think that time scale is before you start.
Yes, definitely. This is what we currently are doing, the like multiple tests, different compositions of membrane, different sets of proteins, equilibrating everything to then choose what can we go in the submission process.
Yeah, that makes sense. I think that's a good plan.
Yeah. Thank you so much, guys.
Certainly. Thank you. I'm happy to hang out here at the podium while people see if they have questions in their souls.
I don't know, it's starting to sound like success.
The virtual podium.
Yep.
Thank you very much, Avi.
Certainly.
All right, thank you, Avi, and all Desres team and PSC team for preparing and setting up this webinar for us. Thanks all who attended, and looking forward to seeing you again in and around Anton.
Thank you all.
Thanks.
Bye. Bye-bye.